2b, Principles of Measurement. 2.10 Instruments. God designed the human senses to provide all essential information for daily life. Early in history, many linear units of measure were based on the dimensions of the human body, e.g., pace, cubit, span, and hand. As society and technology advanced, more accurate methods for measurement were required. Using their God-given intellectual capabilities, men invented the necessary tools to extend their senses and refine their perception. These tools, collectively called instruments, permitted more exact measurements. Instruments are invaluable to modern scientific research because they permit the accurate and precise measurement of quantities that unaided human perception can only estimate, or that are completely outside the range of human senses. For example, lengths and distances can be measured with rulers, as well as with lasers, radar, and sonar. Astronomical distances can be measured from stellar redshifts obtained with telescopic spectrometers, and atomic distances can be measured using instruments such as scanning tunneling electron microscopes and X-ray diffractometers. Besides measuring length, time, and mass, instruments have been developed to measure force, speed, temperature, light intensity, magnetism, electric fields, frequency, and a host of other physical properties. All modern instruments have at least one limitation. They are all man-made. No matter how accurately an instrument can measure and how skillful the user, the tiny variations in dimensions and quality during its construction and the limitations of human perception guarantee that there will always be some error in the measurement. 2.11 Accuracy. How can you be sure when you measure the length of a pencil with a ruler that the observed length is the actual length? The question is answered by a qualitative term called accuracy. Whenever we make a measurement, we compare the object being measured to the graduated scale of an instrument. The instrument is accurate if it produces measurements very close to the actual value. The accuracy of an instrument depends on the quality of its original design and construction and on how well it is maintained. Most scientific instruments can be adjusted so that the error of their measurements is kept within an acceptable limit. Periodic calibration checks are performed that compare an instrument's output to a highly accurate prime standard to verify that the instrument is accurate at one or more points on its scale. Zeroing a laboratory balance is a simple instrument calibration. Obviously, the accuracy of a measurement also reflects the skill of the operator. The contribution of human error to a measurement can be reduced by averaging the results of several measurements that are taken either by the same or by different persons. To make a quantitative assessment of the accuracy of measured data, we must compare the measurement to the actual value or accepted value and determine the error. Error is expressed as the simple difference of the observed and accepted values. The sign of the result indicates whether the observed value is larger, plus, or smaller than the accepted value. The magnitude of the error, or absolute error, is the absolute value of the difference. Knowing the error of measured data is not always as useful as knowing how large the error is compared to the accepted value. In this case, we want to find the relative or percent error, which gives the measurement error as a percentage of the accepted value. Percent error, observed value, accepted value, over accepted value, times 100%, 2.1. You can also find the absolute percent error by substituting the absolute error in the numerator of equation 2.1. 2.12. Precision. Modern handheld calculators can display calculation results to 11 or more digits. Is it appropriate to report your homework problem results to this many figures? The answer is obviously no, but why not? The reason rests on the precision of the measured data given in the problem. Precision is a qualitative term that describes the exactness of a number or measured data. Some physical quantities are known exactly because of the way in which they are defined. The speed of light and the length of a meter are two such quantities. Other numbers can be counted. When we count the number of people in the classroom, we know the number exactly. There are other mathematical quantities that are not exact, but we may express them to any degree of exactness we desire by specifying the number of decimal places to include. These are called irrational numbers. Their values are exact only when we write them using special symbols reserved for irrational numbers, such as the square root bracket, root, the Greek letter pi, ratio of a circle's circumference to its diameter, CD, and the letter e, base of natural logarithms. When an irrational number is written as a decimal, the number of decimal places indicates the precision of the irrational number. Irrational numbers have potentially unlimited precision. Measured data does not have unlimited precision. When we make a measurement with a mechanical instrument, we read the major and minor scale division marks of the instrument. The digits in the measurement based on the scale marks are known for certain, but measurements almost never fall exactly on an instrument scale mark. So, we must estimate the fraction of the distance between the marks. When you use a mechanical metric instrument, one with scale subdivisions based on tenths, measurements should be estimated to the nearest 1/10 of the measurement's smallest decimal increment. For most measurements made in a high school laboratory, this estimated digit is the last, rightmost digit in the measurement. With finer graduations, more certain digits are possible, and the measured data potentially has greater precision. See Figure 2.18. The maximum precision of an instrument is limited by its finest scale subdivisions. The last digit that has any significance in a measurement is estimated. See the discussion of significant digits in the next section. The human act of measurement introduces some uncertainty into every measurement. We will assume for this course that the uncertainty of any measurement is plus or minus half of the place value of the estimated digit. For a meter stick whose smallest subdivision is the millimeter, 0.001 somewhere, the uncertainty is plus minus 0.5 meters or plus minus 0.0005 meters. The uncertainty of most measurements you will make will be much smaller than half the place value of the estimated digit. In actual research, uncertainty is determined by a statistical process. 2.13 Modeling the speed of light. Evaluating Ole Rømer's observations of Io and his data depended on some developing science and technology. In 1675, Christian Huygens had developed an accurate clock that could measure seconds. Giovanni Cassini had formulated a table of predicted sightings of Io, and he had just recently calculated the diameter of the Earth's orbit. All of these pieces of information were necessary to measure the speed of light with any accuracy. Since then, the speed of light has been determined many times by more sophisticated methods. In 1983, this quantity was defined as a constant, c. The speed of light appears in many scientific formulas, like Einstein's famous equation E = mc square. Table 2 to 3 on the next page lists the data for some of the more significant determinations of CE using a variety of techniques. The uncertainties of the measurements, when known, are based on the method by which the speed of light was determined.